Great. Today we are in Unit 3, Day 4, applications of the derivative and higher order derivatives. So some of this is just going to be review because we've seen all different types of word problems before and so forth. So if you ever want to pause and just kind of do it on your own and then check it, feel free to do that as well. So number one, a particle moves straight along the line for t is greater than equal to 0. The position of the particle is given by s of t to the third minus 6t squared plus 9t, where t is measured in seconds and s in meters. Find the velocity at any time t. So we should know that the velocity is the derivative. So s prime, make sure notation. So just don't put v of t like this. Make sure you say where it came from. It came from the first derivative of s of t. All right. And we get 3t squared minus 12t plus 9. Okay, now find the velocity when t equals 2 and t equals 4. Okay, so here, v of 2 and v of 4. Now, this one's not a bad one to do by hand. So like here, we could say 3 and then 2 squared minus 12 times 2, all right, plus 9. All right, that's going to give me 12 minus 24 plus 9. Okay, that's going to be negative 12 plus 9. So this gives me negative 3. And if we're thinking in units, velocity, think the position functions in meters. All right, so this one's going to be meters per second. I do want to recall, like, how can we do this in the calculator, Desmos calculator, just so we can be familiar with it. But you're welcome to put like v of t like this equals 3t squared, all right, minus 12t, all right, plus 9. Okay, now v of, if you want to say v of 4, guess what? They go ahead and give you this answer that's right here, and it's 9. All right, so especially now, this one definitely isn't that hard of a problem, but when the problems are harder and you're able to use a calculator, feel free to use this right here. All right, so let's go back. And we figured out that this one is 9. It's also going to be meters per second. So you can tell like here at 2 seconds that this one's going backwards at a speed of 3 meters per second. And this one's going forward at 9 meters per second. All right, now find all times t when the particle is at rest. Well, when do we know particles at rest? It's when v of t equals 0. All right, so 3t squared minus 12t plus 9. Now, since I already defined v of t up here, you can just keep using v of t. And you said where it came from. Now, one of the first things I noticed, I can divide out a 3. And when I do that, I get t squared minus 4t plus 3. Okay, these should be something that's easily factorable. All right. Again, keep putting equals 0 on it. And we get t minus 1, t minus 3. And I can quickly see you don't necessarily have to set t minus 1 and t minus 3 equal to 0. You can jump to, I know that t equals 1 and t equals 3 from that equation right there. So at 1 second and at 3 seconds is when this particle is at rest. And those are the chances that it can start turning around. Okay, so when is the particle moving in the positive direction? Well, it's when the velocity, and always get in the habit of start writing because a lot of times they'll say justify. I know it doesn't here, but it's when v of t is positive. Okay, or you can even put v of t is greater than 0. Okay, well, think about those two resting points right here. Now, sign lines don't count as work, all right, but I find they're very, very helpful. All right, so I'm going to use one right now. All right, now I like to use the factored form because say if I plug in 0, that's going to be a negative number and that's going to be a negative. So negative times a negative makes positive. All right, something in between here would be 2. 2 minus 1 is positive. 2 minus 3 is negative. So positive times a negative is going to be negative. All right, and then something after would be 4. 4 minus 1 is positive. 4 minus 3 is positive. So positive times a positive is a positive. You can also think of this as a parabola that goes up like this. So on the ends, it's going to be above the x-axis. And here in between 1 and 3, it's going to be below. Okay, so below would mean minus. All right, so when is it moving in the positive direction? All right, it's when we've already said y, when v of t is positive or v of t is greater than 0. Now, pay attention. Up here, we said t is greater than 0. So we don't want to say starting at negative infinity. We want to say starting at 0 to 1. And then it picks back up at 3. Now here's off to infinity. Just pay attention. Did it say to any other time, like in between 2t? And it didn't. So this one's going off to infinity. Now, find the total distance traveled over the interval. All right, later on, there's going to be other ways to solve this, but for right now, what we need to figure out, okay, so from 0 to t. Okay, now this is a little bit different. Total distance traveled versus total displacement. Total displacement is how far did it go from basically time 0 to time 5. Who cares what it did in between? The total distance is we want to know how much it traveled forward, how much it traveled backwards. All right, so we got to put here, we got to put 0, the time. All right. And we're going to go back and use S of t, our position function for this. All right. We're also going to put 5, but I've also got to put where it turned around at 1 and 3. All right. So here we go. Now, again, we're using this position function that's up here. So think about it. If I plug 0 in, I'm going to get 0. So it starts at 0. Now, does it always start at 0? No. It can start somewhere else. All right, so pay attention to that. Now, if I plug in 1, 1 cubed minus 6 times 1 squared plus 9 times 1, that's going to give me 1 minus 6, which is negative 5, plus 9, which is 4. So far, I've gone 4 meters. And if you think about it, okay, it went 4 meters forward. All right, now, what about 3? 3 cubed minus 6 times 3 squared plus 9 times 3. All right, so this is going to make, all right, let's try this for a second. 27, and that's 27. All right, which is 54, I think it is. Okay, so we got 54, and then minus 54. All right, so we go back to 0. So we were traveling backwards another 4 meters. So sorry, I put that little 4. Okay, and now 5 cubed minus 6 times 5 squared plus 9 times 5. All right, I'm just going to grab the calculator right quick. Yes, usually what we would do is we would do this without a calculator, but for time's sake, I'm plugging it in. All right, and I'm just plugging it in here. And we could use Desmos too if we wanted. All right, so here we go. So here we went from 0 to 20, which is 20 meters. So how far did I actually go? Well, 4, 4, and 20 makes a total of, so 4 plus 4 plus 20 is 28 meters. So they went a total of 28 meters is the total distance. Now, if it was just total displacement, it would be 0 to 5. So 0 to 20, it would only be 20 meters. All right. Now find the acceleration at particle time t. Okay, well here, the acceleration is the second derivative. All right. All right, so here, second derivative is going to be 6t minus 12. All right, and we need to find that time at 4 seconds. So 6 times 4 minus 12, 24 minus 12 is going to give us 12. Now, if we're talking about units or they ask us for units, every time you take the derivative, you're basically dividing by seconds again. So seconds squared or meters per second per second. All right, here we go. Okay, when is the particle speeding up and when is it slowing down? All right, when something is speeding up, V of t and A of t have the same sign. When it's slowing down, V of t and A of t have different signs. All right. I always like to write out why. A lot of times, again, like I said, they're going to say, ask you to justify. All right. And this is your justification. All right. Your sign line can't be justification, although we do need a sign line. This is the sign line for V of t up here. We need a sign line for A of t. So I need to take A of t and set it equal to 0. All right, so 6t equals 12, so t equals 2. All right. Okay, and if you think about it, all right, say 1 or 0. If I plug 0 in, this is going to be negative. If I plug in, say 3, 18 minus 12, that's going to be positive. All right, you can also think of this linear, okay? It starts down at negative 12 as the y-intercept, and it goes up. So below the x-axis, then it hits 2, and then goes above the x-axis. All right, so here we go. If you want to think of it, here's where 2 is here. Okay, and then here's where 1 is, and here's where 3 is. All right, so this is the sign line for A of t. Okay, so when is it speeding up? All right, it's going to be speeding up at the same sign. Well, here from 0, remember this started at 0, 0 to 1, this one's positive, this is negative. All right, so this is going to be slowing down. All right, but 1 to 2, 1 to 2, this is negative, 1 to 2, this is negative. So that's speeding up. All right, 2 to 3, it's negative for velocity, but it's positive for acceleration. So 2 to 3, it's going to be slowing down. All right, and then 3 to infinity, look at 3 to infinity, they're both positive here. So therefore, this is speeding up. So we got our when it's speeding up, and we got when it's slowing down. All right, now find the displacement of the particle over the interval from 0 to 8. So notice this is a total different question from E to here. Find the displacement, how much it moves from 0 to 8. Who cares what it does going backwards or forwards? Well, we already know S of t, or S of 0, equals 0. So now we need to find S of 8. All right, 8 cubed minus 6 times 8 squared. All right, plus 9 times 8. Again, I'm just going to throw this in real quickly. Okay, so, all right, 8 cubed minus 6, 8 squared. Oops. There we go. And then plus 9 times 8. All right, 200. Okay, so it went from 0 to 200, so it went 200 meters. All right, it traveled more than that, but that's not the question that it asked us. All right, I've also pulled out a couple of word problems from our book, and I've kind of notated what number and what page they're on as well. All right, a projectile is shot vertically upward from a point 2 meters above the ground with an initial velocity of 24.5 meters a second. The height in meters of the projectile at time t seconds is given by. And you see that they have the 2 meters in here. You see how they have the velocity 24.5, so forth. Find the velocity of the projectile at times t equals 2 and t equals 4. So this is the height of it. All right, to get the velocity, we take the derivative. All right. So if I was finding v of t, this would just be 24.5 minus 2 times that would be 9.8 t. All right. Now, let me show you some things with a calculator because I want you to make sure that you're aware of just the different things you can do with the calculator. All right, so let me share the screen. All right, here we go. So we have a different one. All right, this time we'll put h of t. Okay, 2 plus, whoops, equals 2 plus 24.5 t, all right, minus 4.9 t squared. Okay, we can do different things, and some of these are just trial and error. So knowing that we're trying to find the velocity at 2 seconds, and we know it's the derivative, we can say h prime of 2, and look what we've got. They automatically give us h prime of 2. And I'm going to write this down, guys, is 4.9. And this one's going to be in meters per second. Okay, and then we can do the same thing. If I change this to 4, we get that h prime of 4 is going to be negative 14.7 meters per second. All right. And you can see that I have written them down right here. Okay, so that's how we can use our calculator. It can find the derivative without actually us finding this function right here. Now, if you want to check to make sure it's right, plug 2 into here, see if you get that, plug 4 into it as well, and see if you get that. Okay, when does the projectile reach its maximum height? Maximum height, if you remember, this is a quadratic. When does it? So that's the time. Well, t equals, if you remember, negative b over 2a to find the maximum. So in this case, now a lot of times we like to write this so it's negative 4.9 t squared in order 24.5 t plus 2. So this is our a, that's our b, and that's our c. All right. Now, negative b, so negative 24.5 all over 2a. So 2 times negative 4.9. All right. So here we can find it negative 24.5 divided by 2 times negative. And realize in these calculators, there is a difference between the minus and the negative sign. Negative is right down here at the enter. All right, so there is a difference between them, unlike Desmos. So here I get 2.5. Okay, 2.5 seconds. If I go back and I go to the graph, okay, I can see that it's up here. Now, when you're in the graph, do you see this like graph settings, this wrench on the right-hand side? If you hit that and it's like, I want to go up. So that's up to my y-axis. So you can just take a guess, 50. All right, because it's fine. The width is fine from right here to right here. It's just the height. And so right here, do you see how the time is 2.5? All right, so you can find the maximum on here if it is calculator active. All right, so what is the max height? Well, what is the max height? We actually just saw it there, but to get the max height, you take 2.5 and you plug it in like this. This is a little bit of math one stuff, actually. All right. We just saw it just a second ago, but I'm just looking. It is 32, if I were to plug this back in, 32.625, and it's meters up in the air. All right. When does the projectile hit the ground? All right. Think it goes up and then it hits the ground. All right. So when I go back and I'm just going to look at the calculator on this one. So it goes up, it starts here at 2 meters, or that's our y-intercept, and it goes up to its max height and hits the ground right here. Okay, so when the question is when, so that's time is 5.08034 seconds. All right. Also, when does it hit the ground? That's when S of t, no, H of t, this one's H of t, equals 0. Okay, so it's when that equation is set equal to 0. So how is that replicated? When it hits the x-axis. All right, and what is the velocity of the projectile when it hits the ground? All right, so we take that velocity function that we got up here, and we're basically plugging this in here. All right, so 24.5 minus 9.8, 5.08034. And guys, make sure, of course, rounding, okay? You got to round to 3 decimal places, but that's the final answer. When you're plugging things in, you want to keep a lot of decimal places because this isn't our final answer yet. All right, and we would get an answer. Now, again, you can use Desmos on this. Okay, and here we already have the function in h of t. So here we can just do h prime, and then we plug in that number, 5.08034. And we can tell that it's going to be negative 25.287332. I like to just write them all down. So it's meters per second. And let that make sense for a second. It's coming back down to the ground. But so because it's coming down, it's going to be a negative number. The velocity is going to be negative. All right. So there we go. So a little bit of math one, math two mixed in to some calculus here. All right, here we go. We're going to move right along, get to my other page. Okay, so right here, this is 11A on page 271. A company makes computer chips from square wafers of silicone. It wants to keep the side length of a wafer very close to 15 millimeters, and it wants to know how the area A of X of a wafer changes when the side length X changes. Find A prime of X and explain the meaning. All right, pulling out my notes here. Okay. So here we want to find and explain the meaning. So first off, we don't actually have a formula yet. Okay. Now, area. I see area. Do you see square? Okay. What is the area of a square? Okay. So A of X, area of a square is side squared. You may say base times height, but remember the sides are the same. Okay. So side squared. All right, so here we need to find A prime. Well, A prime of X is going to be 2S. All right, my S's look like 5, sorry. Okay, so now what does this mean? Oh, okay, and it wants to keep the side length of a wafer close to 15 millimeters. All right, so we can actually, now think about this for a second. The units would be millimeters squared. Okay, so the units here, whenever I find them, is millimeters squared per millimeter. All right. Um, okay, so if I wanted to find like the side, like when it's changing, say if I plug in 15, 2 times 15 is going to give me 30. All right. So what this means is, and the derivative is always a rate. Okay. So this is a rate. This is the rate at which the area is increasing with respect. And if you notice, it's always going to be positive because whenever I put in, you're never going to have a negative side length. Whenever I put in a positive number here, it's going to stay positive. And the bigger it gets is the bigger the rate's going to get. So the rate at which the area is increasing with respect to the side. All right. So make sure you know what the meaning of the derivative is. All right. Now, our next one, 12A, page 271. Sodium chlorate crystals are easy to group in the shape of cubes. Pay attention to that. So cubes, by allowing a solution of water and sodium chlorate to evaporate slowly. If V is the volume of sodium chlorate, I'm going to stop there. What is the volume of a cube? Okay. Volume of cube, I'll just say V of T. Yeah, we'll just say V of T, is T cubed. All right. And actually, I got a better idea because they used X right here later on. Let's use X. V of X is X cubed. There we go. So if V is the volume of sodium chlorate crystal cube with a side length X, find dV dx when X equals 3 millimeters. Okay, so dV dx, so 3x squared. All right, it's just the derivative. Okay, they just had a different notation there. And explain the meaning of your answer. All right, so well, what does this mean? All right, again, this is going to be a rate. So it's the rate at which the volume increases as X increases past 3 millimeters. Okay, so like here, this would be millimeters cubed. All right, well, it's going to be millimeters cubed per millimeter. All right, and so here, if I find dV dx when x equals 3, Then I get 3 times 3 squared, and that's 27. Like that. All right. So again, make sure you understand what, and sometimes this can be very difficult, but again, the derivative is a rate, okay? It is a rate. And I also want to take a look at graphs. Now, if you actually have this paper, draw these graphs. Pause it, draw the graphs for a second. Okay, this is found on page, similar graphs are found on page 271, number 5. So looking at the graphs of the velocity function. So these are each of the velocity, we'll say v of t. Okay, when is a particle speeding up and slowing down? All right, well, remember this. When it is speeding up, okay, when it speeds up, a of t and v of t have the same sign. Okay, when it's slowing down, a of t and v of t have different signs. Okay, so here we go. So for v of t, for speeding up on both of these, okay, so speed up. Speed up, so when is it positive and increasing? Okay, it looks like it's positive, that means above the x-axis, and increasing all the way to, we'll just say here, we'll say that's our max right there. So from 0 to 1. Okay, slowing down. Now, when it's positive and decreasing, so decreasing would mean our A of t is negative, all right? Positive and decreasing, it's slowing down, so from 0 to 2. Okay, and then when it's negative, so this is negative and decreasing, these are going to have the same sign. So therefore, from 2 to 3, and actually 2, and look at it, it has an arrow, so we're going to put it infinity. All right, it is decreasing. Now, it could do other things afterwards, but for right now, we'll just say 2 to infinity. All right. Now, let's look at this one. So speed up. Okay, positive and increasing. Well, there's no positive and increasing. This is all slowing down. Okay, so from 0 to 2. All right. Okay, now this is negative and decreasing. We'll just say that ends at 3. Okay, negative and decreasing. So that's speeding up. Those are the same sign. All right, so from 2 to 3. This is negative and increasing. So that's slowing down. That's negative, and then increasing would be A of t would be positive. So 3 to 4. All right, and I'm stopping at 4 because there's no arrow here. This is just, it stops at 4. All right, so be able to look at graphs, be able to look at word problems, velocity functions, acceleration functions. When is it speeding up? When is it slowing down? These are all things that we've hit before, but I wanted to hit again. Also know what the meaning is and what units are for different derivatives, the first derivative, second derivative, and so forth in these word problems. All right, if you have any questions, please come and ask me, and make sure you always do your homework. Thank you.